Welcome back to my channel, another new video. In this video, we're continuing the tree playlist of the Data Structures Algorithms Bootcamp, and we're learning about another type of tree. So the first tree video was Introduction to Binary Search Trees. Second tree video was about self-balancing binary search trees. We learned about AVL trees. And before we move forward and do the questions trees video, like interview questions, what sort of questions are asked, we're going to learn about some other types of trees. So in this video, we're going to focus on segment trees. Very important topic for, let's say, your interview questions, even compared programming and all sorts of things. So let's learn about segment trees. In this video, we'll see what segment trees are, and obviously, just like every other tutorial and concept, before moving on to segment trees, we'll learn about what are the challenges it solves, what is the use case, what type of questions can help you in solving segment tree, like what type of questions use segment trees. So we'll do some nice questions as well, and obviously the code and the notes and everything, assignments can all be found in the description below, so you can check out the code links and everything in the description below. And let's get started. Okay, so segment trees. So we talk about segment trees. Forget about segment tree for now. Let's say we have a question first. Okay, so the question is, given an array A which is equal to something like this. You have 1, 6, 8, 2, 7, 16. Now you're given a question, please find the sum between two indices. Okay, so what are the indices? We all know indices 0, 1, 2, 3, 4, 5. Let's say you're given a question, find the sum of all the elements between the index number 2 and index number 5. So means this all sum. This sum we need to find. 8 plus 2 plus 7 plus 16. Very easy. Now I ask you this question and I'm like, how do you do it? Kunal, it's very simple. Start the pointer from index number 2 and take the pointer till index number end and keep a sum of all this. So in worst case, what we build the time complexity? Worst case would be sum all the numbers. So worst case would be sum all the numbers one by one, O of n. Time complexity for this one. Right? Sounds good? Best case time complexity, you're only asking for one element. Find the sum of all the numbers in between index number 2 and index number 2, which is index number 8. Sorry, number 8 or at index number 2. So this one, for that, time complexity is what? Constant. So worst case, best case, simple way via which you can take the sum. Right. That's the problem. So problem is that O of n is not good enough for us. Okay, not good enough. So we need to solve this question better than O of n, something like O of log n. Okay, so O of n not good enough. Find O of log n solution. And that solution is segment tree. So I'll also tell you when to use segment trees, okay? Right. Okay, so how can we solve it with segment trees, and what is segment tree? Let's take a look at that. Right. So if I talk about segment tree, then let me first briefly tell you what it is, then we'll dive into the infrastructure, architecture, whatever you want to call it, like the theory, implementation, and the intuition, like Kunal, when to use a segment tree. So segment tree basically means, in simple terms, you perform some query on a range. This is very important, on a range. So when you are given questions like find the maximum, so this is an intuition point of view. So when are you going to use segment trees? I'm answering that now. When you are given a question that works on range, like performing a function or a query on a given range. That can be anything. Sum of all the numbers in the range, maximum item in the range, average of the range, minimum item in the range, product of all the numbers in the range, so on and so forth. So types of questions. If interviewer is giving the question, okay, you have an array. Don't worry about how segment trees work right now. Let me first explain to you the basic need for it. Then we'll see how it works and everything. Forget about the, don't worry about how it's structured and how it's happening. We'll do that. So question is given to you. Given an array, find the sum of all the numbers between two indices. Segment tree. Find the product of all the numbers between two indices. Segment tree. Find the maximum number between a range of two indices, like between index number 2 and index number 5. Find the maximum number. Segment tree. Find the average of all the numbers between two indices. Segment tree. So now I hope it is clear when to use segment trees. Okay, move forward. That's one thing. And perform on a range in O of log n time. How we got O of log n? Obviously we will take it. Obviously we'll look at it. Okay. Now, one more thing is that the update method, update function is also O of log n time. Because it doesn't make sense. Let's say, Kunal, you're storing some data in segment tree, let's say range specific data. We don't know what that data is right now. We will take care of it. You will tell us later on. That's fine. But let's assume it's a data structure, so it will have data in it. So we're getting this answer in O of log n time. But what if someone changes the array? Obviously, then segment tree data will also change because array has been changed in. So what is the time complexity it is going to take for changing that data? If that time complexity is O of n, then what is the point of using segment tree? That time complexity is also, by common sense, it's going to be O of log n, because if it was O of n, then there's no point. There's no point until and unless data is not being modified that much. But anyway, how it is O of n for getting the answer? How is it log of n for getting the answer? How is it log of n for updating it? We'll take a look at it right now. Let's see. And the structure of segment tree. Okay. So let's take a look at the example of segment tree. Let's see how segment tree is made and all the properties of segment tree. We talked about, like, I'll formalize the advantages, disadvantages. But let's first take an example. So segment tree, one more thing I'll write over here is segment tree. I'll just write it on the on this page. Segment tree is a binary tree. Binary tree means what? Every node has maximum 2 children, which has information about the intervals as well as the operation we are performing. Interval, info, and operation performing. So interval info can be index number 2 and 6, interval info, and the operation we are performing is, let's say, sum. So both of these information combined, what do we get? Sum of interval from 2 and 7, 2 or 5 or whatever index was. Okay, it will be making much more sense when I draw segment tree. So let me draw segment tree. Let's take an example. Let's say question is, find the sum between any two integers. Sum between any two integers. Let's say array is given to as something like this: 3, 8, 7, 6, minus 2, unsorted array, random array, okay, whatever you want to call it. Can have duplicates also, no problem. Right? Total size of the array n is equal to 8. 1, 2, 3, 4, 5, 6, 7, 8. Indices I'll write down 0, 1, 2, 3, 4, 5, 6, 7. No problem at all. Since it's a tree, so obviously we'll have nodes and stuff. Okay, let's see what the node contains. According to the definition, it's very simple. Node is going to contain two things. Looks like a pokeball. Anyway, node is going to contain two things. it's going to contain the interval information, let's say interval number 1 and 5, for example, and it's going to contain the answer of that interval, the query on that interval. What is the query of the interval? Sum. So by default, the root node is going to have all the intervals. So interval 0 till 7. What is the sum of all the elements from 0 till 7? If you calculate, it's 27. Query interval. This is how every node will look like. Query and interval. Okay. Sounds good? Makes sense? So segment tree, binary tree, and yeah, pretty cool stuff. And every node represents the query and a range. And how we build this binary tree we'll take a look at later. And the root node has the entire array in it. Okay. So how do we form this tree? Root node contains all the information about all the array's elements. And since it's a binary tree, we're just going to divide it every time by 2. And as you may know, if you keep dividing the array by 2, one point of time will come where the array will only have one element. You can't divide it more. That is the base condition. Let's divide it by 2. Okay. So if I divide it by 2, let's say I divide it here, this and this. So array indices 0 till 3, array indices 4 to 7. What is the sum of indices from 0 till 3? If you calculate it, it's 24. What is the sum from 4 till 7? If you calculate it, it's 3. Again divide it. Again divide it. So now you have 0, 3. If you divide it, you'll get what? This and this, this and this. 0, 1, 2, 3 and 4, 5, 6, 7. Divided all by 2. So this is 0, 1, 2, 3, 4, 5, 6, 7. What is the sum? Sum of elements between 6 and 7 is 13. 4 and 5 is minus 10. 2 and 3 is again 13. And 0 and 1 is 11. Okay. Again divided by 2. Now when you divide it by 2, you can see it will only have one element. Index number 0, index number 1, so on and so forth. Index 0, what is the sum of all the numbers from 0 to 0? 3. Sum of all the numbers from 1 to 1? 8, and so on and so forth. That is what segment tree is. Very simple. Okay, so leaf node, you can say here, leaf node, you can say only one element in array, because it makes sense. You cannot divide the array more. Okay, makes sense. Cool. So you already know about the advantages. You can update and you can find the range answer in log of n. How to calculate that answer, we will tell you. I know you may be having a doubt, Kunal, you are finding answers of range from 0 to 3, but how about if you want to find 2 to 5? Where is 2 to 5 in these circles? Some is lying on the left hand side, some is lying on the right hand side. Don't worry, I'll take a look at it. But there's obviously one disadvantage, as you can see over here, extra space. You have to create an entire tree, so that's one disadvantage. So, right, let's see how this works. Like, how can we find the items, like the answer in any range using this tree? One thing you may remember before we move forward to like, okay, Kunal, this is fine, we have made it. But one thing you may remember is, as you can see, if you have watched the trees playlist, the first video of tree, I told you about full binary tree. So segment tree is full binary tree. What is full binary tree? Full binary tree means every node except the leaf node has two children. Every node except the leaf node has two children. So we did this in lecture 1. For a full binary tree, we know that leaf nodes n minus 1, no, not n minus 1, leaf nodes n, and internal nodes n minus 1. Okay, total nodes 2n minus 1. We did this in the previous lecture, so just a recap. Okay, if you want to learn how we are getting this number, check the previous video, lecture number 1. Okay, formed the tree, learnt about advantages, disadvantages, we know when to use it. But now the real question is, how do we calculate the sum? How do we calculate the sum between two indices? Okay, I just created this tree in a prettier way, as you can see over here, for the same example as we had previously in the above question. So the array is equal to 3, 8, 7, 6, minus 2, minus 8, 4 and 9. Okay, indices 0, 1, 2, 3, 4, 5, 6, 7. Looks good. Now let's say this is the tree that we have created. Very simple stuff. So we have to find the sum between two indices. Here you have 3 cases. Okay, you will have 3 cases. So for example, let's say you want to find the query in the interval 2, 6. So 2, 6 is this thing. Okay, let's say that's the question. Sum between 2, 6. So how do we find that sum? So we will see that for 2, 6, since these array indices are divided into 2, 2, then whatever index you may give, index range, you know that sometimes it will be like that index obviously does not lie in the diagram over here because it is divided by 2. So many broken parts of that index will be in different nodes. Okay, sounds good. So let's say you're checking this. You start obviously from checking from root node. So my index range is 2, 6. Is the index range in root node? Yes, it is. Can I just return the answer? No, because the answer has something extra in it. Answer has 0 till 7. So I can't do that. Okay, let's say I move forward. I say 0, 3 or something like that. Okay, 0, 3. Is this containing numbers in my range? Yes, I am asking for 2, 6. I am now at 0, 3. So these two numbers I want. Sorry, not these two numbers. Yeah, these two numbers, 7 and 6. So you can see many intervals may have some parts of your answer. Okay. Similarly, when you go down, you reach, let's say 4, 5, and you'll be like, hey, is 4, 5 and the interval that I want, is that overlapping or having something in common? Yes, 4, 5 is totally inside the answer you want. So I know that minus 10 is definitely going to be a part of my answer. Because it's very common sense. Interval 2, 6, you want the sum. I can say that, for example, this is equal to multiple intervals. Interval 2, 3 plus interval 4, 6 for example, 4,5 plus interval 6,6, etc. Many cases. It can be any case. I'm just giving an example. Example only. So 3 cases, what did we see? Case number 1 is, let's say, what is case number 1? I'll write all the cases down here. Case number 1 is node interval lies inside my query interval. Node interval, which is in the tree, is inside query interval. Example 4,5. This one. Okay. In that case, what do? Just return the answer, because we need it. We have included it, so we need it. Okay. So I'll just say return the answer. Return the value as we need it. Case number 2. We're just seeing the type of possible cases. This is what we did in linked list and other also. Node interval is, let's say, completely outside the query interval. Okay. Is completely outside query interval. Okay. So for example, node start index is greater than the query's end index. Okay. So let's say for 2,6, you are at an interval called 7,8 or something. I want the answer between 2,6. Now I am at an interval that is giving me the sum between 7 and 8. Do I need it? No. I don't need it. Okay. Sounds good? Cool. So what do you do in this question? In this case, what do you do in this case? Return the default value of the query. Are we taking this sum? No, we don't want this sum. So in this case, it is 0. Let's say if you're finding the maximum item between a range, then the default value is going to be equal to what? Integer.min value. Okay. Also, or one more case, if the node end interval is less than query start. Node end less than query start interval. That's also another case. Let's say it lies on the left hand side. Okay. So for example, you're trying to find the answer between 3,5 and you are landing at an index of 0,1. I will remove that. 0,2 I will remove that. 1,2 not needed, but 1,2 is not here. Yeah, anyway. Okay. Very simple. Third point, overlapping. Overlapping. For example, if your query is 2,6, then overlapping can be what? 0,3, this one. That's overlapping. Right? 0,3. It does not have 8 indices, so I'll just put 7 here. Let's say you have 0,3. So example can be 0,3 because it's overlapping, as you can see over here, overlapping. This thing is overlapping. Right? So what do we do in case of overlapping? However it's overlapping, you can ask the left and the right node to give the answers, and then you can just reduce the answer from these two values. Let's see. Okay, so what that basically means is, let's say you're at 0,7. Okay, let's say you start at 0,7 and you're given, let's say, 2,6. Okay, so you go on the left hand side and you're like, hey, or for 0,7 for example, Kunal, what is the case 1, 2 or 3 for 0,7? It is third case, because it is partial overlapping. As you can see, I want 2,6 and it's giving me 0,7. No, it's completely inside it. Like if we have an overlapping, not partial overlapping, this is full overlapping. So this is case number 3. We have overlapping. Like the entire query that I want is inside the answer. So it's going to be like, okay, do one thing, ask your left hand and right hand side. That is what you have to do. Ask the left hand side and right hand side to give their answers and then reduce your answer from this. This is how the recursion tree will grow. So you're like, okay, I will go on the left hand side first. 0,3. This is again overlapping. Again, it will ask left hand side and right hand side. 0,1. This is outside. Case number 2. So ignore. It will stop over here. 2,3. Totally overlapping. Return it. So as you can see, what happened? We started from here 0,3. It automatically removed 0,1. Can you see that? And it only returned the one we want, 2,3. Now we know that the rest of the ones lie on the right hand side of the root, whatever we divided it with. So 4,7. 4,7 is again overlapping. It's going to be like, okay, no problem. Give me the answer of the, give me the answer of your left and right, and we will take it from there. Okay, it will be like left, it's going to be like, so first again, this will, for example, first of all, this will just return 13. Okay, it's very simple. Let me change the color and write it down again. So 2,6, I'm starting from here. Okay, this is what? This is case number 3, overlapping. So it's going to be like, okay, give right hand side and left hand side, give me your answer. Okay, I am inside it overlapping. Some are overlapping, some I need to remove. You give me the answer. Okay, it's going to be like, okay, let me go here first. So 0,3, again case number 3, overlapping. It will be like, okay, let me ask my children. 0,1, this is total ignore. It will return 0. 2,3, it is totally inside 2,6. Return the answer. This will return 13. So the answer will be what? Left plus right is the answer, because we are taking plus. So whatever left answer you get, whatever right answer you get, plus it. I hope that plus is clear why we are adding all the 2 answers from left tree and the right tree, because that's the question. And this logic in blue that I just wrote, you can break down intervals. Okay. So this value here is 13. It will return 13. If like, hey, 0,7 root node, when you divided me by 2 and my left child was 0,3, only 13 exists. That is true. 7 plus 6 is 13. Now it will be like, okay, right hand side. Let's go in the right hand side. 4,7. 4,7, again case number 3, overlapping. Then it will go here. It will go on the left hand side and right hand side. So in the left hand side, it's gonna say 4,5. 4,5 is again totally inside it, so just return -10. And then it's gonna be like, let me try right hand side now. 6,7. 6,7 is again overlapping. It's gonna be on the left hand side. 6, yeah, just return 4. 7 is again case number 3, so just return 0. 4 plus 0, 4. This will value be 4. It will return 4 here. Very simple. Then 10, -10 plus 4, -6. This value is -6. Then -6 plus 13. What is -6 plus 13, or 13 minus 6? 7. Answer is 7. 7 plus 6, 13. minus 2, 11, plus 4 is minus 2, 11, 11 minus 8, 3, plus 4, 7. Simple. Answer. So here you can see that my array 2, 6 was divided into 2, 3 plus 4, 5 plus 6, 6. That is why we are adding all of this. That is why we are adding. Because these are just broken down indices, so we need the sum, so we just need to add. If you want to multiply, you will multiply. If you find the maximum item, you will compare the maximum item of both the two, whatever is maximum return or whatever. Very simple. Question was, let's say find maximum item between 2 and 6. In that case, you will just return whatever the maximum is from these two. Very simple. Cool. Simple segment tree. And how long does it take? Worst case would be log n, because the height of the tree is log n, because it's a binary tree. Cool. Okay. So it's very simple. Nothing else is remaining here. This one thing is remaining: updating. How to update in log time. How to update in O of log n time. So let's say we need to change the index number 3 with 14. Okay. Change index 3 with 14. Index number 3 with 14. Something like that. So index number 3 here we have is, value is 6. We have to change it to 14. So first of all, we will check whether the index that we're trying to change lies in the range or not, in the node interval. Okay. So this is just precaution. Index lies in interval. So interval is what of the array? 0, 7. If yes, what do we need to do? Something you have to take care of it. Something you have to take care here. 3, 7, right? Sorry, 3 I have to update with 14. So you can see 3 is here in the left hand side. It is not in the right hand side. And 3 here, if I talk about 3 in the blue, like this, it is here, here, and here. So you know that in no one level you will have an index in multiple nodes at one single level. Very clear? It's not like if 3 is here, 3 will also be somewhere here. Or if 3 is here, 3 will also be somewhere here or here. No. 3 will only be in one node at a particular level. One node at a particular level. So let's think about it. How to solve this? What are we going to do? We know it lies in 0, 7. Okay. Now we will pass it to our child nodes and just ask them to update. Do you have any other option? No. Because if 3 is here, 3 is here, 3 is here, then these answers will change. You know, these answers will change. If 3 does not lie in the child node, for example here, 3 does not lie in this interval, then don't do anything. Just return whatever value you already originally have. Hence, it will not really update it. But if the value needs to be changed, then you have to update that value, then return it. Very simple. We will write the code and you will understand. So let's say you start from here, you're like, hey, update index number 3. Okay, index number 3 lies in 0, 7. Yes, check left hand side and right hand side. Left hand side will be like, or right hand side will be like, just index 3 lie in right hand side. No, it doesn't. Check left hand side. Index 0, 3 lie in the left hand side. Yes, it does. Okay, then it's going to be like, does it lie in the left hand side or right hand side of this? Check. Does it lie in the left hand side or right hand side of this? 24, 0, 3. It's going to be like, no, not in the left hand side. Yes, in the right hand side. Okay, then it's going to be like, does it lie in the left hand side? So it will just, if it says no, it will just return whatever the original value is, 11. It's going to be like, in 0, 2, 3, does it lie on the left hand side? No. Return the original value. Does it lie on the right hand side? At one point of time, you will have that index in the leaf node. So it will go through the entire tree till the leaf node. So as I'm giving the example, does it lie, now here, this is the base condition. It's going to say that over here, you can say that now the new value, if this is 14. Now the new value is, let's say 14. Okay. So when you go up, okay, so it will be now equal to, let's say 14, and it will return 14. So obviously now the new value for this will be equal to what? Left plus right, 7 plus 14, 21. So it will be 21. Similarly, 11 plus 21, 32. So it will be 32. Similarly, 32 plus 3, it's going to be like, hey, does 3 lie in 4, 7? No, it doesn't. Just return 3. 32 plus 3, 35. Updation, very simple. Start from the top. Check the child. If it is lying totally outside, if my index that I want to update is not lying in the range of that node, just return, because nothing needs to be changed. So just return the value. But if it lies in it, then keep going down, keep going down. In the end, you will find that index, you will update it, and then automatically it will update all the ones like I did right now over here. Plus, 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 plus. So it's following this trail. What is the length of this trail? Log of n. Time complexity, log of n. Very simple. Okay. I did a dry run of the example twice. I did a dry run of update also. I think update should be pretty clear. I explained the steps also. I will write down steps. If yes, okay, then check child nodes. If child range is out, no change in value, just return. In the end, you will reach leaf. Update leaf and recursion will update the tree as we saw in the example. Alright, that's it. Segment 3 finished. Now you can try this concept with the other questions. Find the maximum between two ranges, and this is a very popular question. You get it in interviews. It looks very simple. People are like, oh, it's very simple, I will just do it in O of n. Then the interview is like, do it in log n. Segment 3. One disadvantage, you have to create extra space. Code. Time for coding. Let's code it. Okay, I'm going to create a new file, and you can find the link in the description below. And I'm going to call it trees 3 segment. These are data structures folders I've created, but yeah, you can directly run the code in the browser itself. So the code that I'm going to be writing, you can click on run after forking it, and you can make changes, try it out. So No need to install anything. You can do it on your browser itself. So yeah, people often ask me where's the code. The links can be found in the link to this exact code can be found in the description and also in the pinned comment. So let's see. Create a new file, tree.java or segment tree.java. Okay. Class segment tree, zooming in a little bit and making sure that looks good. You need to create a node first. So node contains data, start interval, end interval, and it has a pointer to left, pointer to right. Simple. Very simple. Private class node. It has a data, it has a start interval, it has a end interval. One more thing I would recommend is try to create these things, because now you are pro. We have done linked list, we have done recursion, we have done trees already, we have done trees. So I would recommend try creating it on your own and then watch the video and see what differently you did. Okay, that is the nice way to learn. Public node, little constructor, I'll say start interval and interval, this dot start interval is equal to start interval and this dot end interval is equal to end interval. Not a problem at all. Okay, that looks good. Now I have my root node, root, and then I have a constructor, segment tree, and in my main what I'm going to have is I'm going to have a, so if I create public static void main here, public static void main, love coding here with no like you can have AI support as I mentioned previously, but yeah, it's pretty cool. You can have 6, 7, and then we had -2, -8, 4 and 9. Segment tree is equal to new segment tree. I'll pass my array in it. So here it will take an array. Okay, sounds good. Cool. So once we have this array, we need to create a tree using this array. Create a tree using this array. This tree you have to create using this array. No problem, I'll create another function. This dot root is equal to construct tree. So I will just create a tree using a construct tree method, and it's going to return the root, and we will just set that root in our root variable. What is construct tree going to have? It will obviously have my array. It will have a start index and end index. Start index is originally 0, end index is length -1. One thing I want you to understand is theory, understanding, explanation, multiple examples, run through, walk through, we have already done. That is where main focus should be. Coding, you can just look at what we have done and just turn that into code now. This is why even though we're doing this in Java, the data structures bootcamp, you can use any other language you want. I am coding in Java, you code in Python and C++. What's the problem? There is no problem. Okay, cool. So we are going to construct this tree. We are going to make this tree. One thing I want to ask you is, what is the time complexity to create the tree? O of n, because you have to calculate every single like half, but for every single one. So you understand, right? If I'm talking about these in the end, you can see that there are n number of elements, O of n, to make tree. Okay, no problem, but that's only once. So in the long term, it will be O of log n for operations. So construct tree is returning a node array int start and end. So what do we do? Some base condition, if start and end, let's say this one, the base condition, if start is equal to end, means we are at the leaf node. Leaf node. So node leaf is equal to new node, and it will have start and end in it. Okay, new node, start and end in it. Data by default will be 0, so that's fine. We will update it later on. That is okay. Start and end. Leaf dot data, not 0, sorry, it will be the number itself, na? The number at index 3, the number at index 2, the number at index 1, the number at index 5. Okay, so leaf dot data is the number at that index. Return leaf. But how the recursion will flow? We are here, we will create a new node with the index we are currently at. Create new node with index you are at. Okay, node is equal to new node, and I'm gonna say the index I'm currently at is start and end. No problem. Created an index and then find the middle. Find the middle, not a problem. Now I will construct the recursion. Node dot left will be equal to what? I can't find this 27 till I go till the leaf. So when we come in return, we will get, let's say, think about recursion. Now think about it as smaller problem. So 27 will be equal to whatever you're getting from left plus whatever you're getting from right. So this current node dot data is whatever you're getting from left plus whatever you're getting from right. This is the beauty of recursion. You don't have to think and just return the node, because it's asking for node, so I have to return the node type. These are all basic recursion concepts. If you have done recursion on my playlist multiple times, I have mentioned it. But we have to update left and right. So no problem. Node dot left is equal to what? Construct tree. Node dot right, again construct tree. For node dot left, start will not change, end will become mid. For the right hand side, start will become mid plus 1. Sorry, start will not change for this one, end will become mid. For the right hand side, start will be mid plus 1. So 3 plus 1, end will not be changed. That's it, tree constructed. Think about this construct tree method. Very simple. Do you want to do a dry run? Let's do a dry run. So if we do a dry run here, let's do a dry run. Okay, here let's say I take a simple example. Let's say A is equal to 3, 4, 9, 12. 3, 4, 9, 2, for example. Let's take it small. So here you can see that it's first going to say for this array 0 comma 0 1 2 3. So 0 comma, or let me take one more item to make it a little bit larger. 7 4. So initially it's going to say, I'm going to take one more item, as you can see over here, and now it's saying is start equal to end. So initially start is what? 0 comma 4. So it's going to be like, no it's not. Okay, create a new node with 0 comma 4. Create a new node with 0 comma 4. Not a problem. 0 comma 4. What do I do next? Next what you need to do is find the mid. So mid is equal to what? 2. And then node dot left is equal to construct tree again with 0 comma 2. So mid is equal to 2. Here it will be again now 0 comma 2. Then it will be like, is 0 equal to 2? Because it's calling the function again. No. Created a new node. That's fine. Find the mid. Mid is equal to 1. Call the left hand side. Find the mid. Mid is equal to 1. Call the left hand side, which is 0 comma 1. That's it. Now it's going to be like, call this, no problem. Again call, is 0 equal to 1? No it's not. Okay, created a new node. Find the mid. Mid is now 0 plus 1 divided by 2, 0. And then it's going to go in the left hand side. Start and end 0. Now it will be, first of all going inside. So it will be like, start equal to 0. Yes it is. Then it creates leaf node. Leaf dot data will be array of start and then return leaf. So leaf dot data will be array of 0, which is 3. Then return this node. Where is this node returned? I have probably mentioned it 1000 times, from where this function was called. So this node, this will be equal to node. So node dot left is equal to this node. Make sense? This arrow, now it is attached to this. Okay. Node dot left is equal to whatever you return, means this node that I just returned. Now it will call right hand side. Right hand side will be again 1 and 1. Same concept will be like, okay, this is equal to 4, like this. It will be returned. So after it's returned, it will be like node dot right is equal to this node over here, 4. After that, once you, for every node, once you have the answer for left and right, you will be like that node's data. Now I have left answer and right answer. So I know the data for that node is equal to left plus right data. 3 plus 4, 7. Set that data as 7. And then return that node from where it was called. Where was it called? From here. And the end, root will be returned with the original answer. Simple, very easy. Should be easy because you are pro at recursion now after watching the playlist. That's how recursion works. Okay. Very simple. You can try it more if you want to dive deep into it. Okay. One more cool thing I want to show you before we move on to the query and update functions is, let's say we create a display function that will display me very nicely. Public void display. Initially it will have nothing. I will call another helper function. Display this dot root. Private void display node. So if you're at a particular node, let's say we have a little string over here. So I say string str initially is empty, and the base condition, if you are at the leaf node, then not the leaf node, for any node, let's say you start from root. So for any node, if node dot left is not equal to null because it's a complete, like I said, tree, then I will just print, for example, I will say string is equal to string plus, let's say, interval is equal to node dot left dot start interval plus node dot left dot end interval plus this, and I can say and data is going to be equal to what? Node dot left dot data. And ladder is over here. String. Make sense? Okay. Should be curly braces. Otherwise, I can say string is equal to string plus, let's say, no left child. Okay. Now, for current node, let's say I have, this is my base condition, like I can just return no current child. For current node, I can say string is equal to, again, I will just copy this. String is equal to interval plus start interval plus this, and data is equal to new node dot data. And this one is going to be two additions over here, not a problem. Some indenting. So current node dot data, and then we're going to have the left and right. So if node dot right is not equal to null, same thing. Right is not equal to null. String is equal to interval node dot right, not node dot left. This will be just node dot start and node dot end. Node dot data, node dot right, and node dot right dot data. That looks good. Otherwise, no right child. I will just in the end print the string, whatever string you have. Now just call recursion. If node dot left is not equal to null, display node dot left. Node dot right is not equal to null, display node dot right. Cool. Very simple. So just a little helper function, like for display. It's not the part of the main algorithm, just for fun I created. We will try to run this and I will show you the workflow and how it's working. But let's move to the main part. So query, how to find query. So public int query, let's say query start index, query end index. I'm just going to say return this dot query. We start from root, query start index, query end index, private int node, query start index, query end index. Right. Query. How do we do query? What are the cases for query? So node, let's say, is completely lying inside the query. So I can say if node dot start interval greater than equal to query start interval and node dot end interval is less than equal to query end interval, In this case, I know that the node is completely lying inside query. So all the items inside this, so if this node is lying inside the query, then we will take all the items in this node node.data. Else if node dot, let's say, start in interval is greater than the query end interval, or node dot end interval is less than query start interval. We have already done this, see over here, bottom right. Nothing new. Query start interval, return 0 in this case because completely outside. No contribution. I have already explained. Otherwise it's overlapping, call the left and right. Otherwise return this dot query left recursion, start index query end index, this dot query node dot right query start index query end index. Query index will not change, right? Why? How can you change query index? And the dry run, the running of this line, we already did when I was explaining the overlap one. See these ones, the red ones. I said this is case 3, case 2. So we already did this, nothing new. Same thing like this will run. That's it. What is remaining now? Update. Let's say index value. For this index, update the value. So update function also we did. We know that it is returning the node value here, and since we need to update the root node, let's say we're not returning the node value, we're just returning the value of the node. Update also we did. You see this in black ink. We did a complete walkthrough of how update function is working, and I wrote it over here is how to update in 3 steps. Check whether it lies in the interval. If yes, then check the nodes and all sorts of things. So I will just do that. We are not rushing anything. We have already covered in this video itself. If index lies in the interval greater than equal to node dot start interval and index is less than equal to node dot end interval, what do we do? Check. If yes, then check the child node. If the child range is out, then no change, just return. Example already done. Index, little indentation error, no problem. Looks good? Right. Now if index is equal to node dot start interval and let's say index is equal to node dot end interval, in this case we are at the base condition here, so I will just update. Node dot data is equal to the value, return node dot data. Otherwise I will just return the answer. Okay, otherwise call left and right and just return the sum of the answers. Otherwise node dot data is equal to, or I can just say int left answer is equal to update node dot left comma index comma new value, which is value, right answer is equal to update node dot right index value, then this current node dot data is equal to left answer plus right answer. That is it. Then return node.data. Okay, this is for this case, for example this one. But otherwise, for this case, otherwise, if let's say it's completely outside, let's say it's completely outside, if it's completely outside, not in this range, then for example this one, I will just return the value. That's it. That is it. Cool. Now we can run this. One mistake I made was I forgot to create the helper function. So this will actually be private and public void update int index with the value, and this dot root dot data is whatever answer I get from the helper. This dot root index value, this will be my helper. It will have a node. Cool. And also now that it's returning an integer, this will be int over here. Okay, it's a little forgot to create the main function and the type, then I had the typo, but I think that looks good. So updating the value and also just returning the, so make sure, right, when you're returning it and it's storing it in a type integer, then here also you have to have the type integer because of recursion rule. Whatever you type you're returning should be the type of the return type. Okay, and I also had some little typos over here and there, like this leaf was left for example, so fix those typos. But yeah, looks good. Index equal to node interval, so on and so forth. I followed these 3 rules over here, how to update in log time. So pretty standard stuff. And the display function is also pretty simple. I'm just taking the node and interval, displaying it in a prettier format. That's it. Should be pretty straightforward. We have done so complex, parentheses type questions and stuff, so this should be no problem. And I created a new main file over here, keeping it separate from segment tree. Good practice. So just let's try to run this tree.display. There you go. So root here, as you can see, so for this node here, it's saying 0, 3, 24, 0, 3, 24, and 0, 7. Over here it says 27, as you can see, and 4, 7 is giving the data 3. Okay, 13. Oh, sorry, 3. Okay, so one thing I can do is in display, this last line I don't need in display. Right child, don't need this. Yeah, in the right I don't need this, and then new line. Run this. Now looks good. So root node, left child, right child, 0, 7, 27, 0, 3, 24, 4, 7, 3, 0, 7, 27, 0, 3, 24, 4, 7, 3. Now for 0, 3 as a root node, it is 24, 24, 0, 1 left hand side, 2, 3 right hand side, 0, 1 left hand side, 2, 3 right hand side. Make sense? Simple display. Just a little fun extra thing I wanted to show you. Now let's say I forget the display and I get my query answer. system.out.println tree.query find the sum This is why we create helper. Now you can see I can't pass the root node, so I just have to pass the numbers, and internally it will call another function that will pass root node. You have to make sure that the person who is running the program does not interact much with how the program is made. They should only be able to see, the answer. So what do you want to do? Index number, let's say 1 to index number 6. Let's try that. What is the answer? Index number 1 to 6. 8 plus 6 plus 7 minus 2 minus 8 plus 4. 15. Getting 15 here. Very cool. Log of n. That's it. Have fun now. And lastly, I would say the code, this entire thing can be found in the description. Notes link can be found in the description. Many people say notes are not opening. If on the 51st lecture you are saying notes are not opening, you cannot even clone the simple GitHub repository, then I can't help you. There are people in the comment section, Kunal, object-oriented programming notes on GitHub repository are not opening. If you cannot clone a GitHub repository, then not me. No one in this world can help you. Forget about me. Let's say lecture, object-oriented programming, notes, all the PDF notes are here. Some people are saying these are not opening. That might be true. In this case, let's say this is opening. But in some cases, it's not opening, for example. I can't help you. Simply clone the repository in your system. Star it as well. That'd be nice. But just clone it. You will have all the PDF in your system. But anyway, the code for this, directly you can find the link in the description. You can click on run and you can run it on your own system after clicking fork, update it and do all sorts of things, run it on your system. And 3 things I would like you to do: like right now, comment right now, share this video. So you can take a screenshot. You can use hashtag DSA with Kunal and join the Learning Public Initiative. So if you at least like and comment, that will help boost the algorithm and more people will find these free courses. And you can take a screenshot, share hashtag DSA with Kunal. And if you have any comments, like any questions, leave those in the comment section below as well. But I'm not charging you any money for this. So the best way to say thank you is liking and commenting. So it helps the YouTube algorithm and sharing with your friends and on social media. Thanks a lot for watching. I'll see you in the next one. Have a great day. Bye.